Hello there, and welcome to tonight's peaceful journey through the cosmos. I am delighted you've chosen to spend these gentle moments exploring the universe's quiet mysteries with me. As you settle in for rest, wherever you may be, let's embark on a soothing voyage through space and time, discovering the serene wonders that float silently above us each night. Take a deep breath and allow yourself to relax completely. Tonight, we'll float gently through cosmic phenomena that will ease your mind into peaceful slumber. The universe holds countless tranquil secrets, and I'll share them with you in soft, measured tones designed to help you drift away into restful sleep. The night sky above you right now contains approximately 200 billion trillion stars. That is more stars than there have been heartbeats from every human who has ever lived. Each one of these distant suns follows its own peaceful path through space, moving in slow, graceful arcs that take millions of years to complete. As you breathe slowly and deeply, imagine yourself floating among these gentle giants of light, each one a warm, comforting presence in the vast darkness. Our own star, the Sunday, completes one rotation around the center of our galaxy every 230 million years. This cosmic year, as astronomers call it, represents a journey of incredible scale and duration. The last time our solar system was in this exact position in the galaxy, dinosaurs had not yet appeared on Earth. This slow, steady movement continues regardless of our daily concerns, a reminder that the universe operates on timescales that dwarf our momentary worries. As you continue to relax, consider that every atom in your body, except for hydrogen, was created inside a star. You are quite literally made of stardust. The calcium in your bones, the iron in your blood, the carbon that forms the foundation of your DNA, all were forged in the nuclear furnaces of dying stars billions of years ago. When massive stars reached the end of their lives and exploded as supernovae, they scattered these elements across space, eventually forming new stars, planets, and ultimately you. You are intimately connected to the cosmos in the most fundamental way possible. The Moon, our celestial companion, moves away from Earth at approximately 1.5 inches per year. This incredibly slow drift has been happening for billions of years. When the Moon first formed, it was much closer to Earth, and days were considerably shorter. Over geological time, the Moon's gravitational interaction with Earth has gradually slowed our planet's rotation and pushed the Moon farther away. This gentle ongoing dance between Earth and Moon continues tonight as you rest, a cosmic ballet performed in slow motion. Space between stars is not truly empty but filled with an incredibly thin mist of atoms and molecules. In the average cubic meter of interstellar space, there are only about 1 million atoms. For comparison, a cubic meter of air on Earth contains about 10 circumflex 25 atoms. This near-perfect vacuum is more empty than anything we can create in laboratories on Earth. Yet even in this profound emptiness, slow chemical reactions occur, gradually building complex molecules that may one day become part of new planets and possibly new life. The Andromeda Galaxy, our nearest large galactic neighbor, is approaching our Milky Way at about 68 miles per second. While this might sound alarming, the collision won't occur for another 4 billion years. When it does happen, the two galaxies will pass through each other in a cosmic dance lasting hundreds of millions of years. Despite containing hundreds of billions of stars each, the vast distances between stars mean that direct stellar collisions will be extremely rare. The galaxies will eventually merge into a single, larger elliptical galaxy, which astronomers have already named Milkdromeda. As your breathing becomes slower and more regular, consider the profound silence of space. Sound requires a medium through which to travel, and the near-perfect vacuum of space provides no such medium. If you could stand on the Moon and watch Earth rise over the lunar horizon, you would experience absolute silence. No sound would reach your ears, no matter how massive the cosmic events occurring around you. This eternal quiet pervades most of the universe, a peaceful stillness that has existed since the beginning of time. Jupiter, the giant protector of our solar system, acts as a gravitational shield for Earth. Its immense mass attracts and captures many comets and asteroids that might otherwise threaten our planet. In 1994, we observed comet Shoemaker, Levy 9 crash into Jupiter, leaving scars in its atmosphere larger than Earth itself. Without Jupiter's protective influence, life on Earth might have been extinguished by cosmic impacts long ago. Tonight, Jupiter continues its vigilant patrol, silently safeguarding our world as you sleep. The rings of Saturn, one of the most beautiful sights in our solar system, are surprisingly thin. While they extend over 175,000 miles in diameter, they are typically only about 30 feet thick. If you built a scale model where Saturn's rings were shrunk to the size of a football field, they would be thinner than a sheet of paper. These magnificent rings consist of countless particles of ice and rock, each following its own orbit around the giant planet, creating patterns of incredible complexity and beauty. Venus, often called Earth's twin due to its similar size, rotates backwards compared to most planets in our solar system. A day on Venus, one complete rotation, takes longer than a year on Venus, one complete orbit around the Sunday. This means that if you could stand on Venus's surface, you would see the Sunday rise in the west and set in the east, and it would take 117 Earth days between each sunrise. This leisurely rotation creates a unique rhythm, unlike anywhere else in our solar system. Neptune, the most distant major planet in our solar system, has winds that reach speeds of up to 1,200 miles per hour, faster than the speed of sound on Earth. Yet these tremendous winds blow through an atmosphere so cold that methane freezes into ice crystals, creating beautiful blue clouds that drift through the planet's upper atmosphere. Despite being 2.8 billion miles from the Sunday, Neptune generates more heat internally than it receives from our star, a mystery that continues to puzzle planetary scientists. As you sink deeper into relaxation, imagine the asteroid belt between Mars and Jupiter. This region contains millions of rocky bodies, remnants from the early solar system that never coalesced into a planet. Despite Hollywood depictions, the asteroid belt is mostly empty space. If you were to stand on one asteroid, the nearest one would likely be hundreds of thousands of miles away, too distant to see with the naked eye. The total mass of all asteroids in the belt combined is less than our moon, spread across a region of space billions of miles wide. Titan, Saturn's largest moon, has lakes and rivers like Earth, but they're filled with liquid methane and ethane instead of water. Rain falls from orange skies, creating river valleys and filling lake basins in a cycle remarkably similar to Earth's water cycle, but at temperatures of -290 degrees Fahrenheit. This alien yet familiar world represents one of the most Earth-like places in our solar system, despite its profoundly different chemistry. The surface of Mars preserves a record of the solar system's violent early history. Unlike Earth, where weather and geological activity have erased most ancient impact craters, Mars's thin atmosphere and limited geological activity mean that craters billions of years old remain visible. Walking on Mars would be like walking through a museum of the solar system's past, with each crater telling a story of cosmic collisions from eons ago. Europa, one of Jupiter's moons, likely harbors a liquid water ocean beneath its icy surface. This hidden ocean may contain twice as much water as all of Earth's oceans combined. Tidal forces from Jupiter's gravity keep this ocean liquid, despite the moon's distance from the Sunday. In the depths of this dark ocean, volcanic vents on the seafloor might create conditions similar to those where life first emerged on Earth. As you rest tonight, consider that alien life might exist right now in the hidden oceans of this distant moon. The Kuiper Belt, extending beyond Neptune's orbit, contains millions of icy bodies left over from the solar system's formation. Pluto is just one of many objects in this vast ring of frozen worlds. Some of these objects have highly elliptical orbits that take them far into the outer darkness before bringing them back toward the Sunday. Sedna, one such object, takes about 11,400 years to complete one orbit, spending most of its time in the lonely darkness, far from the Sunday's warmth. Comets are often described as dirty snowballs, but this simple description masks their importance in cosmic history. These icy wanderers from the outer solar system may have delivered much of Earth's water and organic molecules, essential ingredients for life. Each time a comet approaches the Sunday, It loses some of its mass, gradually shrinking over millions of years, until nothing remains but a trail of dust along its orbital path. This dust contributes to meteor showers when Earth passes through these ancient comet trails. The Oort cloud, a sphere of icy bodies surrounding our solar system, extends nearly halfway to the nearest star. This vast cloud contains trillions of comet-like objects, preserved in deep freeze since the solar system's birth. Occasionally, gravitational perturbations send one of these objects falling toward the Sunday, becoming a long-period comet that might not return for thousands or millions of years. The Oort cloud represents the true edge of our solar system, a boundary between our Sunday's gravitational domain and interstellar space. As your muscles continue to relax and your mind quiets, consider the phenomenon of planetary migration. The giant planets of our solar system likely formed in different positions than where we see them today. Over millions of years, gravitational interactions caused them to slowly spiral inward or outward, reshaping the architecture of our planetary system. This migration may have sent asteroids and comets careening through the inner solar system, possibly delivering water to Earth and creating the conditions necessary for life. Mercury, the innermost planet, experiences the most extreme temperature variations in our solar system. During its day, temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead. During its night, temperatures plummet to minus 290 degrees Fahrenheit. Yet in permanently shadowed craters near its poles, water ice exists, preserved for billions of years in these cosmic freezers just millions of miles from the Sunday. The Great Red Spot on Jupiter is a storm that has raged for at least 350 years, possibly much longer. This storm is so large that 3 Earths could fit inside it. The storm's winds blow at speeds of up to 400 miles per h-hour, yet it maintains its distinctive oval shape decade after decade. Recently, astronomers have noticed the spot is shrinking, transforming from an oval to a more circular shape. One day, perhaps centuries from now, this iconic feature may disappear entirely. Io, another of Jupiter's moons, is the most volcanically active body in the solar system. Its surface is constantly remade by sulfur-rich lava, flows that create a landscape that looks like a cosmic pizza. Some of Io's volcanic plumes shoot material 250 miles above its surface, higher than the International Space Station orbits above Earth. This volcanic activity is driven by tidal heating from Jupiter's immense gravity, which literally stretches and squeezes the moon as it orbits. As you drift closer to sleep, imagine the delicate balance that keeps Earth habitable. Our planet orbits within the habitable zone, sometimes called the Goldilocks zone, where liquid water can exist on a planet's surface. If Earth were just 5% closer to the Sunday, it might have suffered Venus's fate, becoming a runaway greenhouse. If it were 5% farther away, it might have frozen solid like Mars. This narrow range of orbital distances that permits liquid water and life as we know, it seems remarkably small when considered against the vastness of space. The solar wind, a stream of charged particles flowing from the Sunday, creates a bubble around our solar system called the heliosphere. This bubble extends far beyond Pluto's orbit, partially shielding us from interstellar radiation. The Voyager spacecraft, launched in 1977, have recently crossed the boundary of this bubble, becoming humanity's first interstellar travelers. They carry golden records containing sounds and images from Earth, messages in bottles cast into the cosmic ocean. Enceladus, a small moon of Saturn, shoots geysers of water, ice hundreds of miles into space from its south pole. These geysers originate from a subsurface ocean, kept liquid by tidal heating. Some of this water ice forms one of Saturn's rings, creating a direct connection between the hidden ocean and the beautiful ring system. Organic molecules have been detected in these plumes, suggesting that the ingredients for life exist in this distant moon's hidden sea. The axial tilt of planets creates their seasons, and each world's tilt tells a story. Earth's modest 23.5-degree tilt creates our familiar seasonal cycle. Uranus, however, is tilted at 98 degrees, essentially rolling on its side as it orbits the Sunday. This extreme tilt means that each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. Scientists believe a massive collision early in the solar system's history knocked Uranus onto its side, a cosmic accident that created one of the solar system's most unusual worlds. As sleep approaches, consider the dance of binary asteroids. Many asteroids are actually two bodies orbiting each other as they journey around the Sunday. These cosmic pairs waltz through space, bound together by mutual gravitational attraction. Some are nearly equal in size, while others consist of a large primary with a small moon. Studying these binary systems helps scientists understand how asteroids form and evolve, providing clues about the early solar system's chaotic history. The zodiacal light, a faint glow visible in dark skies after sunset or before sunrise, is caused by sunlight reflecting off countless tiny dust particles orbiting the Sunday. This dust comes from comets and asteroid collisions, creating a thin disk of material in the plane of the solar system. Ancient astronomers called it the false dawn, not understanding that they were seeing the debris of cosmic collisions illuminated by sunlight. Mars once had rivers, lakes, and possibly oceans. Dried river valleys, lake beds, and mineral deposits that form only in water tell the story of a warmer, wetter Mars billions of years ago. Something caused Mars to lose most of its atmosphere and water, transforming it from a potentially habitable world into the cold, dry desert we see today. Understanding what happened to Mars helps us appreciate how precious and fragile Earth's habitability truly is. The moons of our solar system display incredible diversity, from volcanic Io to icy Europa, from thick atmosphered Titan to heavily cratered Callisto. Each moon is a unique world with its own story. Our solar system contains over 200 known moons, and we're still discovering new ones. These moons range from tiny captured asteroids only a few miles across to bodies larger than Mercury. Each represents a natural experiment in planetary formation and evolution. Trojan asteroids share Jupiter's orbit, clustered at stable points 60 degrees ahead and behind the giant planet. These asteroids have remained in these positions for billions of years, trapped by the combined gravitational forces of Jupiter and the Sunday. Mars, Neptune, and even Earth have their own Trojan asteroids, cosmic companions that perpetually maintain their distance, neither approaching nor receding, locked in gravitational equilibrium. As your breathing deepens and sleep draws near, picture the Perseid meteor shower, which occurs each August when Earth passes through the debris trail of Comet Swift-Tuttle. These meteors, no larger than grains of sand, enter Earth's atmosphere at 37 miles per second, creating bright streaks of light as they burn up. What we call shooting stars are really tiny pieces of ancient comets, transformed by friction into brief moments of beauty. The solar system's planets orbit in nearly the same plane, a consequence of their formation from a rotating disk of gas and dust. This flat configuration means that from Earth, the planets appear to move along a narrow path across the sky, the ecliptic. Ancient astronomers noticed this celestial highway and used it to track planetary movements, developing calendars and navigation systems that connected human civilization to cosmic rhythms. Ceres, the largest object in the asteroid belt, is now classified as a dwarf planet. This world, about the size of Texas, may contain more water than Earth, locked in ice beneath its surface. Bright spots on Ceres, visible from the Dawn spacecraft, are deposits of salt left behind as briny water erupted from below and sublimated in the vacuum of space. These features suggest that even small worlds can remain geologically active billions of years after their formation. The phases of the Moon have influenced life on Earth for billions of years. Many marine organisms synchronize their reproductive cycles with lunar phases. Corals spawn in mass during specific moon phases, creating underwater blizzards of new life. Some birds use the Moon for navigation during migration. The Moon's gravitational pull creates tides that have shaped coastal ecosystems and may have played a crucial role in the evolution of early life. Venus's atmosphere is so dense that the pressure at its surface equals that found 3,000 feet underwater on Earth. This crushing atmosphere is composed mainly of carbon dioxide, with clouds of sulfuric acid. The extreme greenhouse effect has created surface temperatures hot enough to melt lead. Venus serves as a cautionary tale about the power of greenhouse gases, showing what can happen when a planet's climate spirals out of control. As you continue to relax, imagine standing on Pluto's surface. The Sunday would appear as an extremely bright star, providing only 1/1600th the light Earth receives. Yet even this dim sunlight is enough to drive seasonal changes on Pluto, causing nitrogen ice to sublimate and refreeze as the dwarf planet follows its elliptical orbit. A day on Pluto lasts 6.4 Earth days, meaning you would experience a very slow sunrise and sunset in the dim, frozen landscape. The solar system is moving through space at approximately 514,000 miles per h relative to the cosmic microwave background radiation. Our entire planetary system, along with the Sunday, orbits the center of the Milky Way galaxy. Additionally, our galaxy moves through space as part of the local group of galaxies, which itself moves toward the Great Attractor, a gravitational anomaly hundreds of millions of light years away. Even as you lie still, you are participating in this cosmic journey through space. Meteorites found on Earth provide direct samples of other worlds. Some meteorites originated on Mars, blasted into space by ancient impacts, and eventually falling to Earth. Others come from the asteroid Vesta, or the Moon. These cosmic travelers carry information about the formation and evolution of their parent bodies. By studying meteorites, scientists can analyze materials from across the solar system without leaving Earth. Each meteorite a message from distant worlds. The interplanetary magnetic field, carried by the solar wind, creates a complex magnetic environment throughout the solar system. This field interacts with planetary magnetic fields, creating magnetospheres that protect planets from charged particles. Earth's magnetosphere extends of thousands of miles into space, deflecting solar wind and cosmic rays. Without this magnetic shield, Earth's atmosphere might have been stripped away long ago, as apparently happened to Mars. As drowsiness embraces you, consider that our solar system is recycled material. The Sunday and planets, formed from the debris of earlier generations of stars. The nebula that gave birth to our solar system was enriched with heavy elements from supernovae, stellar winds, and planetary nebulae. We are part of a cosmic recycling program that has been operating for billions of years, transforming stellar ash into new stars, planets, and life. The length of a day on Earth is gradually increasing. Fossil evidence shows that 620 million years ago, a day lasted only 21.9 hours. The Moon's tidal forces slowly transfer angular momentum from Earth's rotation to the Moon's orbit, simultaneously slowing Earth's spin and pushing the Moon farther away. In the distant future, Earth and Moon will be tidally locked, with one side of Earth always facing the Moon, and days and months will be the same length. Spacecraft have revealed that many asteroids are not solid rocks, but rather rubble piles held together by weak gravity. These bodies are collections of boulders, rocks, and dust that coalesced after collisions shattered larger asteroids. Their low density and high porosity make them very different from the mental image most people have of asteroids. Understanding their structure is crucial for any future attempts to deflect potentially hazardous asteroids. The heliosphere breathes with the solar cycle. Every 11 years, the Sunday's activity waxes and wanes, affecting the entire solar system. During solar maximum, increased solar wind pressure causes the heliosphere to expand. During solar minimum, it contracts. This breathing motion affects cosmic ray levels throughout the solar system and may influence cloud formation and climate on Earth, connecting our planet's weather to the Sunday's magnetic heartbeat. Triton, Neptune's largest moon, orbits backwards compared to Neptune's rotation, suggesting it was captured from the Kuiper belt. This captured moon is slowly spiraling toward Neptune and will be torn apart by tidal forces in about 3.6 billion years, possibly forming a spectacular ring system around the ice giant. Triton's nitrogen geysers and young surface show that even captured, frozen worlds far from the Sunday can remain geologically active. as sleep gently takes hold. Rest peacefully knowing that you are part of an extraordinary cosmic story. The atoms in your body have traveled across billions of years and vast distances to be here, now arranged in the unique pattern that is you. Tonight, as you sleep, the universe continues its patient unfolding. Stars are born, planets orbit, and comets trace their ancient paths through the darkness. You are safe, you are connected to something immense and beautiful, and you are exactly where you belong in this vast, peaceful cosmos. The gentle rotation of Earth carries you through space as you rest. Our planet spins at about 1,000 miles per hour at the equator, though you feel no sensation of this movement. This rotation creates the cycle of day and night that has regulated life since its beginning. As you sleep, you are being carried eastward toward tomorrow's sunrise, participating in the same rotation that has occurred billions of times throughout Earth's history. Saturn's moon Mimas bears an enormous crater that makes it resemble the Death Star from Star Wars. This crater, named Herschel, is 80 miles wide on a moon only 246 miles in diameter. If Earth had a crater proportionally as large, it would stretch from New York to Los Angeles. The impact that created Herschel nearly shattered Mimas entirely. That this small moon survived such a catastrophic collision demonstrates the role of chance in shaping the worlds of our solar system. The Van Allen radiation belts surround Earth like invisible donuts of charged particles trapped by our planet's magnetic field. These belts protect us from solar radiation, but pose challenges for spacecraft and astronauts passing through them. The particles spiral along magnetic field lines, creating auroras when they interact with our atmosphere near the poles. These beautiful light displays are Earth's magnetic field made visible, a reminder of the invisible forces that protect our world. As you sink deeper into peaceful sleep, consider the concept of Lagrange points, positions in space where gravitational forces balance perfectly. 5 such points exist in the Earth Sunday system, where objects can maintain stable positions relative to both bodies. The James Webb Space Telescope orbits the L2 point, 1,000,000 miles from Earth, where it can observe the universe while staying aligned with Earth and Sunday. These gravitational sweet spots represent the hidden architecture of orbital mechanics. Titan's thick atmosphere creates a greenhouse effect that warms the surface by about 21 degrees Fahrenheit. Without this atmosphere, Titan would be even colder than it already is at -290 degrees. This atmosphere is so dense that a human could strap on wings and fly through it powered by muscle alone. The low gravity and thick air would make personal flight possible on this alien moon, though the extreme cold and lack of oxygen would require substantial life support. The solar system's ice giants, Uranus and Neptune, generate more heat than they receive from the Sunday. This internal heat source remains mysterious, possibly resulting from gravitational compression, radioactive decay, or exotic chemistry deep within these worlds. The fact that worlds so far from the Sunday can generate their own heat suggests that habitable conditions might exist in unexpected places throughout the universe. Phobos, Mars's largest moon, orbits so close to the planet that it completes 3 orbits in a single Martian day. From Mars's surface, Phobos would appear to rise in the west and set in the east, moving visibly across the sky. This moon is slowly spiraling toward Mars and will either crash into the planet or break apart into a ring system in about Wuxi L-lion years. Watching Phobos from Mars would provide a constant reminder of the dynamic, ever-changing nature of planetary systems. The Cassini spacecraft revealed that Saturn's rings are raining material onto the planet at a rate that could drain them completely in lion years. This ring rain consists of water ice particles pulled down by Saturn's gravity and magnetic field. The rings we see today may be temporary features, cosmically speaking, suggesting that Saturn may have had different ring systems throughout its history, each one forming and dissipating over millions of years. As your mind quiets and your body relaxes completely, picture the serene dance of shepherd moons within Saturn's rings. These small moons orbit within gaps in the rings, their gravity-keeping ring particles confined to narrow bands. Prometheus and Pandora shepherd the narrow F-ring, while Pan clears the NK gap. These tiny worlds maintain order in the chaos of billions of ring particles, creating the sharp edges and intricate structures that make Saturn's rings so magnificent. The solar system's planets can be divided into two distinct groups that formed under different conditions. The inner rocky planets formed close to the Sun, where only materials with high melting points could condense. The outer gas giants formed beyond the frost line, where water and other volatiles could freeze, allowing them to grow massive enough to capture hydrogen and helium from the solar nebula. This fundamental division shaped the architecture of our planetary system. Comet Lyushitsy Jan Gerasimenko, visited by the Rosetta spacecraft, has a rubber duck shape formed by two lobes connected by a narrow neck. This comet releases about kilograms of water per second when near the Sun, along with organic molecules including glycine, an amino acid. The discovery of organic compounds on comets supports the idea that these icy wanderers may have seeded early Earth with the building blocks of life. The interstellar medium between stars contains complex organic molecules including sugars and amino acids. These molecules form on the surfaces of tiny dust grains where atoms can meet and react. Radio telescopes have detected over different molecular species in space, including ethyl alcohol and formaldehyde. The universe appears to be a vast chemical laboratory, creating complex molecules that could serve as precursors to life wherever conditions permit. As sleep embraces you, know that somewhere in the solar system right now, dust devils spiral across Mars, storms rage on Jupiter, and ice volcanoes erupt on Enceladus. While you rest peacefully, robotic explorers continue their lonely vigils, sending back data about worlds we've only recently begun to understand. Each discovery adds another piece to the cosmic puzzle, revealing the solar system as a dynamic, evolving place of continuous wonder. The nice model of solar system evolution suggests that Jupiter and Saturn once crossed a RBE orbital resonance, causing gravitational chaos that reshaped the outer solar system. This event may have scattered Uranus and Neptune outward, sent comets flying in all directions, and triggered the late heavy bombardment that cratered the Moon and inner planets. Our seemingly stable solar system has a dramatic history of gravitational violence and migration. Venus rotates so slowly that its day is longer than its year, and it rotates in the opposite direction to most planets. If you could survive on Venus's surface, you would experience sunrise once every Yoyochi Earth days, but the sun would rise in the west and set in the east. This backwards, leisurely rotation may result from a massive impact early in Venus's history, or from tidal effects over billions of years. The boundary between the solar system and interstellar space is not a sharp edge, but a complex region called the heliopause. Here, the solar wind meets the interstellar medium, creating a turbulent boundary layer. The Voyager spacecraft have shown that this boundary is not smooth but rippled and dynamic, constantly shifting as the solar system moves through interstellar space. Crossing this boundary, the Voyagers became humanity's first interstellar ambassadors. Rest peacefully as your journey through the solar system continues in dreams. You have traveled from the sun's blazing surface to the frozen depths of the Kuiper Belt, from volcanic moons to ringed planets, from ancient impact basins to newly formed comets. The solar system is your cosmic neighborhood, filled with wonders that dwarf Earth yet remain connected to your world through gravity, light, and the shared history of formation from a collapsing nebula 4 billion years ago. 继续生成到60,000字符. Mars has the largest volcano in the solar system, Olympus Mons, which rises 6.6 英里, less above the surrounding plains, nearly 3 times the height of Mount Everest. This massive shield volcano is 374 英里 less in diameter, roughly the size of Arizona. Its slopes are so gentle that if you stood on them, the horizon would seem flat. Olympus Mons grew so large because Mars lacks plate tectonics, allowing lava to pile up in one location over billions of years. The asteroid Psyche appears to be the exposed iron core of a protoplanet that lost its rocky outer layers in ancient collisions. This metallic world offers a unique opportunity to study a planetary core directly, something impossible on Earth, where the core lies thousands of miles beneath our feet. NASA's Psyche mission will explore this iron world, potentially revealing secrets about how planetary cores form and differentiate. Jupiter's moon, Ganymede, is the largest moon in the solar system, larger than the planet Mercury. It is the only moon known to have its own magnetic field, suggesting a liquid iron core. Beneath Ganymede's icy surface lies an ocean that may contain more water than all Earth's oceans combined. This ocean is sandwiched between layers of ice, creating a complex interior structure unlike anything on Earth. The dwarf planet Eris, discovered in Lansendine Wu, is more massive than Pluto and helped trigger the reclassification of Pluto as a dwarf planet. Eris takes Wu by years to orbit the Sun, following a highly elliptical path that carries it from Sen-Shabar to Jio-Shabar times Earth's distance from the Sun. At its most distant, Eris experiences temperatures approaching absolute zero, making it one of the coldest known objects in the solar system. As you drift deeper into sleep, imagine the gentle sublimation of cometary ice in sunlight. As comets approach the Sun, their ice is transformed directly from solid to gas, creating the glowing coma and tail that make comets so spectacular. This process releases ancient material frozen since the solar system's birth, including water that may have filled Earth's oceans and organic molecules that could have sparked life's beginning. The moon's surface preserves footprints from the Apollo astronauts that will remain visible for millions of years. With no atmosphere to create wind and no water to cause erosion, the lunar surface changes only through the slow accumulation of microscopic meteorite impacts. The footprints, rover tracks, and equipment left behind serve as monuments to human exploration, virtually unchanged since they were created decades ago. Saturn's hexagonal storm at its North Pole is one of the solar system's most mysterious features. This 6-Jan-sided jet stream is about 800 uni less, across with winds blowing at 900 uni less per hour. The hexagon has persisted for at least several decades, possibly much longer. Scientists recreate this pattern in laboratory experiments by rotating fluids at different speeds. But the exact mechanism maintaining Saturn's hexagon remains partly mysterious. The solar system contains numerous ocean worlds hidden beneath icy crusts. Europa, Enceladus, Titan, and possibly Ganymede, Callisto, and Triton all likely harbor subsurface oceans. These hidden seas contain more water than exists on Earth's surface. Some may have hydrothermal vents on their ocean floors, creating conditions similar to those where life began on Earth. As you sleep, these dark oceans exist in perpetual night, possibly teeming with undiscovered forms of life. Sedna, a distant dwarf planet, follows an extremely elliptical orbit that takes it from Chishuleo times Earth's distance, from the Sun to nearly Ichen times that distance. One orbit takes about Ichen Sibai years. Sedna's unusual orbit suggests it may have been influenced by a passing star early in the solar system's history, or by an undiscovered massive planet in the far outer solar system. This frozen world spends most of its time in the lonely darkness between the Kuiper belt and the Oort cloud. The solar wind carves out a cavity in interstellar space called the heliosphere, protecting our solar system from much of the galaxy's cosmic radiation. This magnetic bubble extends far beyond Pluto, partially shielding Earth from high-Zen energy particles that could damage DNA and affect evolution. The heliosphere pulses with the 11 Jan-year solar cycle, breathing in and out as solar activity waxes and wanes. Rest peacefully knowing that while you sleep, meteoroids no larger than grains of sand continuously rain down on Earth, most burning up harmlessly in the atmosphere. About yobai tons of extraterrestrial material falls to Earth each day, gradually adding mass to our planet. Over geological time, this cosmic dust has contributed significantly to Earth's bulk, connecting our world to the broader cosmos through a gentle, continuous rain of stellar debris. The rings of Jupiter, discovered in Ichen Jiobai Tsushijio, are so faint they're invisible from Earth, without special equipment. These rings consist of microscopic dust particles, knocked off Jupiter's inner moons by meteorite impacts. Unlike Saturn's bright ice rings, Jupiter's rings are dark and composed of rocky material. They represent a more subtle form of planetary decoration, a whisper rather than Saturn's shout. Uranus's moon Miranda displays the most bizarre geology in the solar system, with enormous canyons, terraced layers, and a jumbled surface, suggesting it may have been shattered and reassembled. Verona Rupes, a cliff on Miranda, drops Sierra straight down, 10 times deeper than the Grand Canyon. This tiny moon's dramatic features remain mysterious, possibly resulting from tidal heating or ancient impacts that nearly destroyed it. As your consciousness fades into dreams, consider that our solar system is middle-gen aged, born 70 billion years ago. The Sun has about 1 billion years of stable hydrogen fusion remaining. Our cosmic neighborhood has already experienced half its lifespan, having witnessed the formation of planets, the emergence of life, and the rise of intelligence capable of understanding its own cosmic context. The dwarf planet Makemake, discovered in Laontsen Wu, has no atmosphere, despite being large enough to potentially retain one. When Makemake passes in front of distant stars, astronomers expected to see the star's light fade gradually if an atmosphere existed. Instead, the star's light vanished abruptly, proving Makemake lacks even a thin atmosphere. This frozen world exemplifies the diversity of conditions in the outer solar system. Comets have influenced human history and mythology throughout civilization. The appearance of bright comets has been interpreted as omens, recorded in ancient texts, and depicted in art. Halley's Comet appears in the Bayeux Tapestry depicting the Norman conquest of Ytending. These cosmic visitors connect human culture to astronomical cycles, reminding us that we have always looked to the skies for meaning and wonder. Sleep comes gently as you float among worlds both familiar and strange. From Mercury's sun-Jan's scorched surface to Neptune's frigid winds, from the asteroid belt's rocky fragments to the Oort cloud's icy sentinels, you have toured a solar system of incredible diversity and beauty. Each world tells its own story of formation, evolution, and destiny. Together they form the cosmic family to which Earth belongs. The universe beyond our solar system unfolds in layers of increasing wonder and mystery. As you continue your peaceful journey towards sleep, let's venture beyond the familiar planets and moons to explore the vast cosmic ocean that surrounds our small island of worlds. Breathe slowly and deeply as we drift outward into the serene darkness between the stars. Our nearest stellar neighbor, Proxima Centauri, lies 4.24 light-years away, a distance so vast that light itself, the fastest thing in the universe, takes over 4 years to make the journey. If you could travel at the speed of the Voyager spacecraft, it would take you 70,000 years to reach this closest star. Yet in cosmic terms, Proxima Centauri is practically next door, a neighbor in the vast city of stars we call the Milky Way galaxy. Proxima Centauri hosts a planet, Proxima b, orbiting within its habitable zone, where liquid water could exist. This world, slightly larger than Earth, orbits its red dwarf star every 11.2 days. Because red dwarfs are so dim, the habitable zone lies much closer than Earth's distance from the Sunday. Proxima b may be tidally locked, with one side in eternal daylight and the other in perpetual night, creating a world of permanent sunset at the terminator line between light and dark. As your muscles relax and tension melts away, consider that most stars in our galaxy are red dwarfs, smaller and cooler than our Sunday. These stellar embers burn their fuel so slowly that they will shine for trillions of years, far longer than the current age of the universe. When the universe is hundreds of billions of years old and other stars have long since died, red dwarfs will continue their patient glow, the last lights in an aging cosmos. Binary star systems, where two stars orbit each other, are common throughout the galaxy. Some binary pairs orbit so closely that they share atmospheres, trading stellar material in a cosmic dance. Others are separated by distances greater than our entire solar system, taking thousands of years to complete one orbit. Planets in binary systems would experience double sunrises and sunsets, with days of complex patterns as two suns trace different paths across the sky. The star Betelgeuse, visible as the red shoulder of Orion, is a red supergiant nearing the end of its life. This massive star has swollen to enormous proportions. If placed at the center of our solar system, its surface would engulf the orbits of Mercury, Venus, Earth, and Mars. Betelgeuse will explode as a supernova sometime in the next 100,000 years, briefly shining as bright as the full moon in Earth's sky, visible even during daylight. As you sink deeper into relaxation, imagine stellar nurseries where new stars are born. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one such stellar nursery. Within its glowing clouds of gas and dust, gravity pulls material together, forming protostars that will eventually ignite nuclear fusion. The nebula glows with the light of young, hot stars that have recently emerged from their dusty cocoons, illuminating the surrounding gas in brilliant colors. The pillars of creation in the Eagle Nebula stand as cosmic monuments to the star formation process. These towering columns of gas and dust, several light years tall, are slowly being eroded by stellar winds from nearby young stars. Within these pillars, hidden from view, new stars are forming in dense pockets where gravity overcomes the outward pressure of gas. These stellar nurseries are simultaneously being destroyed and giving birth, a cycle of creation and destruction played out over millions of years. Brown dwarfs occupy the twilight zone between planets and stars. Too small to sustain hydrogen fusion like true stars, yet too large to be planets. These failed stars glow dimly with the heat of their formation and slow gravitational contraction. Some brown dwarfs have storms and weather patterns, like giant planets, while others have their own planets orbiting them. These cosmic in-betweeners challenge our definitions of what constitutes a star versus a planet. The concept of the habitable zone extends beyond individual stars to the galaxy itself. Our solar system orbits within the galactic habitable zone, far enough from the galactic center to avoid intense radiation and frequent supernovae, yet close enough to contain sufficient heavy elements for planet formation. This galactic sweet spot may be crucial for the development of complex life, adding another layer to the cosmic coincidences that allow us to exist. As drowsiness embraces you, picture rogue planets drifting through interstellar space, unbound to any star. These lonely worlds were likely ejected from their birth systems by gravitational interactions. They wander through eternal darkness, their surfaces frozen, yet some may retain internal heat from radioactive decay or residual formation energy. Subsurface oceans could exist on these rogue worlds, possibly harboring life in the darkness between the stars. Neutron stars represent matter in its most extreme form. A teaspoon of neutron star material would weigh as much as Mount Everest. These city-sized remnants of massive stars spin rapidly, some rotating hundreds of times per second. Their surfaces have gravity so strong that mountains can be no more than a few millimeters high. Time passes measurably slower on their surfaces due to gravitational time dilation, a consequence of Einstein's relativity. Pulsars, rotating neutron stars that emit beams of radiation, serve as cosmic lighthouses. The Crab pulsar, remnant of a supernova, observed in 1054 CE, rotates 30 times per second, its beams sweeping past Earth with clockwork precision. These natural timekeepers are so regular that they rival atomic clocks in accuracy. Some pulsars have planets orbiting them, worlds that formed from the debris of the supernova or were captured later, experiencing the strangest skies imaginable. The interstellar medium between stars contains vast clouds of alcohol. Ethyl alcohol, the same type in alcoholic beverages, exists in enormous quantities in space. One cloud near the center of our galaxy contains enough alcohol to supply 300,000 pints of beer to every person on Earth every day for 1 billion years. These organic molecules form on dust grains where atoms can meet and react, demonstrating that complex chemistry occurs throughout the cosmos. As you breathe slowly and peacefully, consider stellar winds that blow from stars like invisible hurricanes. Our Sunday loses about 4 million tons of material every second through its solar wind over its lifetime. This adds up to less than 0.01% of its total mass. Massive stars have much stronger winds, sculpting bubble-like cavities in the interstellar medium and enriching space with heavy elements forged in their cores. The local bubble is a cavity in the interstellar medium surrounding our solar system, likely carved out by ancient supernovae. This bubble of hot, thin gas extends for hundreds of light years, creating a cosmic void through which we travel. The walls of this bubble contain denser gas and dust, sites of ongoing star formation, triggered by the compression from expanding supernova remnants. Star clusters come in two main varieties, each telling different stories about stellar evolution. Open clusters like the Pleiades contain hundreds of young stars born from the same nebula, still traveling together through space. Globular clusters contain hundreds of thousands of ancient stars packed into spherical swarms, orbiting galaxies like bees around a hive. These different cluster types preserve records of star formation across cosmic history. The Hyades cluster, visible as the V-shaped face of Taurus the Bull, is the nearest star cluster to Earth. Its stars are slowly drifting apart, destined to disperse into the galaxy over the next few 100 million years. Light from the Hyades takes 153 years to reach us, meaning we see these stars as they were when your great-great-grandparents were alive. A reminder that looking into space is always looking back in time. Variable stars pulsate, changing their brightness in regular or irregular patterns. Cepheid variables, named after the prototype star Delta Cephei, have a relationship between their pulsation period and luminosity that makes them cosmic distance markers. By measuring how long a Cepheid takes to pulse, astronomers can determine its true brightness and thus its distance, a technique that helped establish the scale of the universe. Let your mind quiet as you consider cosmic dust, tiny particles smoke that drift between stars. This dust, made of carbon, silicon, and other elements, dims and reddens starlight, creating the dark lanes visible in the Milky Way. Yet this same dust is essential for planet formation and life, providing surfaces where molecules can form and materials from which rocky worlds are built. The zodiacal light visible after sunset or before dawn is sunlight scattered by dust in our solar system. But a similar phenomenon occurs throughout the galaxy, where starlight, scattered by interstellar dust, creates a faint glow. This galactic light pollution makes it challenging to observe the most distant universe, yet it also traces the structure and composition of our cosmic neighborhood. As sleep approaches, rest in the knowledge that new stars are being born throughout the galaxy right now. In the Carina Nebula, massive stars are emerging from their birth clouds. In the Rosette Nebula, stellar winds are carving cavities in glowing gas. In countless smaller, darker clouds invisible to our telescopes, low-mass stars like our Sunday are quietly beginning their long lives. The galaxy is a vast ecosystem of stellar birth and death. Type-year supernovae serve as standard candles for measuring cosmic distances. These explosions occur when white dwarf stars accumulate too much mass and undergo catastrophic thermonuclear detonation. Because the physics determining the explosion is consistent, all Type-year supernovae have nearly the same peak brightness, allowing astronomers to measure distances to galaxies billions of light-years away. The Chandrasekhar limit defines the maximum mass a white dwarf star can have before it collapses. Named after Subramanian Chandrasekhar, who calculated at age 19. This limit is about 1.4 times the mass of our Sunday. Beyond this mass, electron degeneracy pressure cannot support the star against gravity, leading to either collapse into a neutron star or explosion as a supernova. Stellar black holes, formed from the collapse of massive stars, typically have masses between 3 and 20 times that of our Sunday. These invisible objects reveal themselves through their gravitational effects on companion stars or by the X-rays emitted as they devour surrounding material. The nearest known black hole is about 1,000 light-years away, close enough to study, but far enough to pose no threat. As your breathing becomes deep and regular, imagine the cosmic recycling that enriches the galaxy. Every atom heavier than hydrogen in your body was forged in stars. The calcium in your bones came from supernova explosions. The iron in your blood was created in the cores of massive stars. You are literally made of star stuff, connected to every star that has ever lived and died in our galaxy's history. White dwarf stars are the glowing embers of sun-like stars, slowly cooling over trillions of years. These Earth-sized objects contain about as much mass as the Sunday compressed to incredible density. A sugar cube-sized piece of white dwarf material would weigh as much as a car. Eventually, white dwarfs will cool to become black dwarfs, invisible and cold, though the universe is not yet old enough for any black dwarfs to exist. The ring nebula in the constellation Lyra shows us our Sunday's probable future. This planetary nebula, despite its name having nothing to do with planets, formed when a dying star expelled its outer layers, creating a colorful shell of gas around the remaining white dwarf. In about 5 billion years, our Sunday will create a similar nebula, briefly decorating our corner of the galaxy before fading into darkness. Carbon stars glow with a distinctive red color due to carbon compounds in their atmospheres. These dying giants are manufacturing carbon in their cores and dredging it to their surfaces. The carbon they expel enriches the interstellar medium, eventually becoming part of new planets and possibly life. Every carbon atom in your body, the fundamental element of organic chemistry, was created in such stellar furnaces. The galactic halo surrounds our Milky Way like an enormous sphere of ancient stars and dark matter. This halo extends hundreds of thousands of light-years from the galactic center, containing globular clusters that orbit the galaxy like satellites. Some of these clusters are nearly as old as the universe itself, preserving stellar populations from the cosmos's youth. As you drift toward dreams, picture the galaxy's spiral arms, not solid structures, but traffic jams of stars and gas. Stars move in and out of spiral arms over millions of years, temporarily bunching up like cars in highway congestion. These density waves trigger star formation, creating the bright, young stars that outline the spiral pattern we see. Our Sun has passed through spiral arms many times during its journey around the galaxy. The galactic center hosts a supermassive black hole called Sagittarius, weighing Li, or lion times our Sun's mass. Stars near the galactic center orbit at incredible speeds, some moving at the speed of light. Despite its enormous mass, this black hole is currently quiet, accreting material at a modest rate. Occasionally it flares as it consumes gas clouds, or unfortunate stars that venture too close. Fast radio bursts are mysterious millisecond, duration pulses of radio waves from distant galaxies. These brief signals carry as much energy as the Sun emits in days, yet their cause remains uncertain. Some may come from magnetars, neutron stars with incredibly strong magnetic fields. Others might signal cosmic events we haven't yet imagined. Each detection adds another piece to this cosmic puzzle. Relax completely as you consider the local group, our galactic neighborhood containing over known galaxies. The Milky Way and Andromeda are the giants of this group, with dozens of smaller dwarf galaxies orbiting them like moons orbit planets. The entire local group is about lion light-years across, bound together by gravity, moving through space as a unit toward the Great Attractor. The Magellanic Clouds, visible from Earth's southern hemisphere, are irregular dwarf galaxies orbiting the Milky Way. These galaxies are connected to our galaxy by a stream of gas called the Magellanic Stream, material pulled from them by tidal forces. Star formation in the Magellanic Clouds provides astronomers with nearby laboratories for studying stellar evolution in environments different from our galaxy. Dwarf galaxies are the universe's most common galaxy type, though their dimness makes them hard to detect. Some contain only a few thousand stars, held together by dark matter. These galactic building blocks merge over time to form larger galaxies. Our Milky Way shows evidence of past mergers, with streams of stars marking where smaller galaxies were absorbed and digested over billions of years. The concept of galactic cannibalism describes how larger galaxies grow by consuming smaller ones. The Milky Way is currently absorbing several dwarf galaxies, their stars becoming part of our galaxy's halo. This process is gentle and slow. Stars rarely collide even when galaxies merge. Instead, the galaxy's stars intermingle, creating new patterns and structures over millions of years. As sleep gently embraces you, know that you're made of atoms forged in stars throughout the galaxy's history. Elements created in different stellar environments have come together in you: hydrogen from the Big Bang, carbon from red giants, oxygen from massive stars, and heavier elements from supernovae. You are a collection of cosmic history, a gathering of atoms with stories spanning billions of years. Ultra-Gen luminous X-Gen ray sources puzzle astronomers with their intense emissions. These objects shine hundreds of times brighter than theory predicts for stellar Gen mass black holes. They might be intermediate Gen mass black holes, bridging the gap between stellar black holes and supermassive ones. Or they could be stellar Gen mass black holes consuming material at extraordinary rates. Each discovery challenges our understanding of extreme physics. Millisecond pulsars spin so fast they threaten to tear themselves apart. These cosmic speedsters have been spun up by material falling from companion stars, reaching rotation rates of hundreds of times per second. Their surfaces move at appreciable fractions of light speed, experiencing extreme relativistic effects. These natural particle accelerators create conditions impossible to replicate in Earth laboratories. The interstellar medium contains complex organic molecules that form the building blocks of life. Amino acids, the components of proteins, have been detected in meteorites and comets. Polycyclic aromatic hydrocarbons, complex carbon-gen-based molecules, are abundant throughout the galaxy. This cosmic chemistry suggests that the ingredients for life are widespread, awaiting the right conditions to assemble into living systems. Breathe peacefully as you consider that our galaxy rotates differentially, with inner regions orbiting faster than outer ones. This differential rotation winds up spiral arms and mixes stellar populations over time. The Sun's current position in the galaxy results from Archer-complete orbits since its formation, a cosmic journey of a billion years that has carried us through varied galactic environments. Stellar streams trace the paths of disrupted galaxies and star clusters. The Sagittarius stream wraps around the Milky Way multiple times, marking where a dwarf galaxy is being torn apart by tidal forces. These streams preserve fossil evidence of galactic mergers, allowing astronomers to reconstruct our galaxy's violent history and predict its future evolution. The thick disk of the Milky Way contains older stars that have been scattered from their original orbits by gravitational interactions. These stars tell stories of the galaxy's turbulent youth when mergers and collisions were more common. Their chemical compositions and orbits provide clues about conditions in the early galaxy and how it evolved into the relatively peaceful spiral we see today. Hypervelocity stars race through the galaxy at speeds exceeding galactic escape velocity. These stellar speedsters were likely ejected from the galactic center by interactions with the supermassive black hole. They travel so fast that they will eventually leave the galaxy entirely, destined to wander intergalactic space alone. Some hypervelocity stars may carry planets, taking entire solar systems on a one-Jian-Wei journey out of the galaxy. As you sink into peaceful slumber, rest knowing that the galaxy continues its patient rotation while you sleep. Stars are born in nebulae, live out their lives fusing hydrogen into helium, and die in spectacular explosions or quiet fading. This cycle has continued for over 6 billion years and will persist for trillions more. You are witnessing a brief moment in this vast cosmic story. The galactic bulge at the Milky Way's center contains ancient stars formed when the galaxy was young. This dense region hosts complex dynamics, with stars on chaotic orbits influenced by the central bar structure. The bulge preserves a record of the galaxy's formation, containing some of the oldest stars we can observe. Studying these ancient stars reveals how galaxies assembled in the early universe. Galactic winds driven by supernovae and stellar winds can expel gas from galaxies entirely. These outflows regulate star formation by removing the raw material needed to form new stars. In small galaxies, these winds can strip away most of the gas, effectively shutting down star formation. This feedback mechanism helps explain why galaxies have the sizes and stellar populations we observe. Dark matter halos surround galaxies like invisible cocoons, extending far beyond the visible stars. The Milky Way's dark matter halo may extend over 1 million light-years from the galactic center, containing most of the galaxy's mass. This invisible matter governs galactic rotation and holds galaxy clusters together. Though we cannot see dark matter directly, its gravitational influence shapes everything we observe. Continue drifting towards sleep as you contemplate molecular clouds, the coldest places in the galaxy. These vast clouds of molecules and dust have temperatures only a few degrees above absolute zero. Within their dark depths, gravity slowly pulls material together, eventually triggering star formation. These stellar nurseries are simultaneously stellar graveyards, enriched with heavy elements from previous generations of stars. The galaxy contains bubbles blown by stellar winds and supernovae. The local bubbles surrounding our solar system is just one example. These cavities in the interstellar medium channel cosmic rays and affect star formation in neighboring regions. The galaxy is filled with these bubbles, creating a cosmic foam structure that influences how matter and energy flow through interstellar space. Magnetic fields thread through the galaxy, guiding cosmic rays and affecting star formation. These fields are amplified by galactic rotation and turbulence, creating complex patterns that we're only beginning to map. Polarized light from distant stars reveals these magnetic field directions, showing how magnetism shapes processes throughout the galaxy. Sleep peacefully knowing that while you rest, light from distant stars continues its journey across space. Photons that left stars decades, centuries, or millennia ago arrive at Earth tonight, carrying information about their sources. Each photon is a messenger, a packet of information about conditions in distant parts of the galaxy. The night sky is filled with these travelers, each one a connection between you and the cosmos. 已生成约24000字符，继续生成已达到6000字符。The concept of metallicity in astronomy refers not to metals as we commonly think of them, but to any element heavier than hydrogen and helium. Stars with higher metallicity formed more recently from gas enriched by previous stellar generations. The older stars have very low metallicity, preserving the composition of the early universe. This cosmic enrichment process has gradually increased the complexity of matter throughout the galaxy. Planetary nebulae, despite their misleading name, mark the death throes of sun-Jan-like stars. These beautiful shells of gas glow in spectacular colors as they expand into space. The Cat's Eye Nebula, the Helix Nebula, and thousands of others decorate the galaxy like cosmic flowers. Each one represents a star's final gift to the cosmos, enriching space with elements that will form new stars and planets. As your consciousness fades, picture stellar associations, loose groups of young stars moving together through space. These associations formed from the same molecular cloud, but lack the gravitational binding of true star clusters. Over millions of years, they disperse into the galaxy, their member stars going separate ways. Our Sun may have been born in such an association. Its siblings, now scattered across the galaxy. Wolf-Gen stars are among the most luminous and hottest stars known, with surface temperatures exceeding Wu-Chan degrees Celsius. These massive stars have powerful stellar winds that strip away their outer layers, exposing hot interior regions. They live fast and die young, existing for only a few million years before exploding as supernovae. Their powerful winds enrich surrounding space with heavy elements. The initial mass function describes the distribution of stellar masses when stars form. For every massive star born, hundreds of low-Jan mass stars form. This universal pattern appears consistent across different environments, suggesting fundamental physics governs the star formation process. Understanding this distribution helps astronomers predict stellar populations and galactic evolution. Symbiotic binary stars involve a red giant and a white dwarf in a complex relationship. The white dwarf accretes material from the giant's stellar wind, occasionally erupting in nova explosions. These systems demonstrate the varied ways stars interact, exchanging material and energy in cosmic partnerships that can last millions of years. Rest peacefully as you consider that the galaxy contains stellar graveyards where ancient stars have died. White dwarfs, neutron stars, and black holes mark where stars once shone. These compact objects continue to influence their surroundings through gravity and radiation. The galaxy is layered with history, each generation of stars building upon the legacy of those that came before. Microlensing occurs when a star passes in front of a more distant star, its gravity focusing the background star's light. This effect allows astronomers to detect planets, brown dwarfs, and other dark objects that would otherwise remain invisible. Each microlensing event is unique and unrepeatable, a cosmic alignment that reveals hidden components of our galaxy. The thick and thin disks of the Milky Way represent different epochs of galactic history. The thin disk contains younger stars and most ongoing star formation. The thick disk holds older stars, possibly formed during a more turbulent period or from a merged satellite galaxy. These overlapping populations create the complex structure we observe today. Galactic archaeology uses stellar compositions and movements to reconstruct the Milky Way's history, like archaeologists piecing together ancient civilizations from artifacts. Astronomers use stars as fossils to understand galactic evolution. Each star preserves information about when and where it formed, creating a distributed record of galactic history. As sleep takes hold, know that you are part of the galaxy's ongoing story. The atoms in your body have traveled through interstellar space, been incorporated into multiple generations of stars, and participated in the chemical evolution that makes life possible. You are not separate from the cosmos, but an integral part of its continuing transformation. Blue straggler stars appear younger than they should be, shining with hot blue light in old star clusters. These stars likely formed from stellar mergers or mass transfer in binary systems, gaining new fuel that extends their lives. They demonstrate that stellar evolution can take unexpected paths, creating stars that seem to defy aging. The period-Zen luminosity relationship of Cepheid variables revolutionized our understanding of cosmic distances. Henrietta Swan-Leavitt discovered this relationship in Ichenjobai Shirap, providing the first reliable method to measure distances beyond our galaxy. This cosmic yardstick revealed that the universe extends far beyond the Milky Way, fundamentally changing our perspective on our place in the cosmos. Flare stars experience sudden, dramatic increases in brightness due to magnetic activity. These flares can double a star's brightness in minutes, releasing enormous amounts of energy. Red dwarf flare stars are particularly common, their flares potentially affecting any orbiting planets. These stellar tantrums remind us that even seemingly stable stars can be unpredictable. Let your thoughts quiet as you consider cosmic rays accelerated by supernova remnants. Shock waves from stellar explosions act as natural particle accelerators, boosting atomic nuclei to near light speed. These cosmic rays fill the galaxy, creating a high Zen energy background that influences everything from atmospheric chemistry to DNA mutation rates. The gold belt is a ring of young stars tilted relative to the galactic plane, possibly created by an ancient supernova or collision with a molecular cloud. Our solar system sits near this belt, surrounded by stellar associations and star-Jan-forming regions. This local structure affects our view of the galaxy and our exposure to supernovae and stellar winds. Mirror variables are pulsating red giants that change brightness over periods of months to years. The prototype, Mirror itself, varies by a factor of each yen in brightness during its Sensenard-Zan day cycle. These stars are losing mass rapidly, surrounded by shells of expelled material. They represent a phase our sun will experience in its distant future. Sleep approaches as you float among the stars, each one a sun with its own story. Some stars are ancient, formed when the galaxy was young. Others are newborns, still wrapped in their natal clouds. Together, they create the galactic ecosystem that has nurtured the development of planets and life. The galactic tide exerts a gentle pull on our solar system, stretching the Oort cloud and occasionally sending comets toward the inner solar system. This tidal force results from the differential gravitational pull across our solar system's extent over millions of years. This subtle influence shapes the orbits of distant solar system objects. X-gen ray binaries produce intense X-gen ray emission as material falls from a normal star onto a compact companion gen, a white dwarf, neutron star, or black hole. The infalling material heats to millions of degrees, creating some of the galaxy's most energetic phenomena. These systems serve as laboratories for studying matter under extreme conditions. Carbon planets might exist around carbon-rich stars, worlds where diamond and graphite replace the silicate rocks familiar on Earth. These hypothetical planets would have fundamentally different geology and chemistry. Their surfaces might be covered in hydrocarbons, with diamond mountains and tar seas, representing alternative possibilities for planetary composition. Rest peacefully knowing that somewhere in the galaxy right now, new planets are forming in protoplanetary disks. Dust grains collide and stick together, gradually building pebbles, rocks, and eventually planets. This same process that created Earth continues throughout the galaxy, potentially creating new worlds where life might one day emerge. Stellar coronae, the hot outer atmospheres of stars, produce X-gen rays and drive stellar winds. Our sun's corona reaches temperatures of millions of degrees, far hotter than its visible surface. Understanding stellar coronae helps predict space weather and assess the habitability of planets around other stars. The galaxy rotates with a flat rotation curve, meaning stars at different distances orbit at similar speeds. This unexpected behavior led to the discovery of dark matter, as visible matter alone cannot explain the observed rotation. The galaxy's rotation reveals the presence of vast amounts of invisible matter shaping its dynamics. As you drift into dreams, you join the cosmic dance of matter and energy that has continued for billions of years. Stars form, planets coalesce, and life emerges wherever conditions permit. You are both observer and participant in this grand cosmic evolution, connected to every star and atom in the galaxy through the fundamental forces that govern all existence. 继续生成至600004伏. Tsai T Tauri stars represent the adolescent phase of Sun-gen-like stars, still contracting toward the main sequence. These young stars exhibit violent flares and strong stellar winds. Many have protoplanetary disks where planets are actively forming. Observing T Tauri stars provides insights into our own solar system's youth, when the Sun was more active and planets were still assembling. The metallicity gradient across the galaxy shows that inner regions are more enriched in heavy elements than outer regions. This gradient results from the inside-gen-out formation of the galaxy, with star formation and stellar recycling proceeding more rapidly in denser, inner regions. This chemical gradient affects the types of planets that can form at different galactic locations. Runaway stars travel at high speeds relative to their surroundings, ejected from stellar clusters or binary systems. Some runaway stars create bow shocks as they plow through interstellar gas, visible in infrared light. These stellar exiles journey alone through space, no longer bound to their birthplaces, carrying any planets with them on lonely voyages through the galaxy. The concept of stellar generations describes how each cycle of star formation builds upon previous ones. Population the third stars, the first stars in the universe, contained only hydrogen and helium. Population the third stars formed from gas slightly enriched by the first generation. Population I stars like our Sun formed from gas enriched by multiple generations, containing the heavy elements necessary for rocky planets and life. Herbig Gen Harrow objects mark where jets from young stars collide with surrounding gas. These glowing shock fronts trace stellar outflows, revealing the hidden activity of star formation. They change visibly over years and decades, allowing astronomers to watch cosmic evolution in real-time time. These dynamic structures demonstrate that the galaxy is alive with ongoing stellar birth. As your breathing slows to match the rhythm of sleep, consider that photons from across the galaxy are arriving at Earth this very moment. Some left their sources when human civilization was young. Others began their journeys before Earth existed. Each photon carries information across time and space, connecting distant events to this present moment. Stellar populations in globular clusters show multiple generations of stars, contrary to earlier beliefs that all stars in a cluster formed simultaneously. These multiple populations suggest complex formation, histories, possibly involving multiple star-gen-forming episodes, or enrichment from massive stars. Globular clusters are not simple stellar families, but complex communities with rich histories. The thin disk of the Milky Way undulates like a flag in a breeze, a phenomenon called galactic warping. This warp might result from gravitational interactions with satellite galaxies or dark matter. Our solar system rides this gentle wave, oscillating above and below the galactic plane over millions of years, experiencing varying cosmic environments during each oscillation. Blue compact dwarf galaxies experience intense bursts of star formation despite their small size. These galactic firecrackers convert gas into stars at prodigious rates, creating numerous hot, blue stars that dominate their light. They may represent a phase that all galaxies experience, periods of rapid growth punctuating longer quiet phases. Sleep comes gently as you float in the vast spaces between stars. The interstellar medium, though nearly empty by Earth standards, contains the seeds of future stars and planets. Every atom in this thin gas has a history stretching back to the Big Bang or to the nuclear furnaces of long-gone dead stars. You breathe air made from this same cosmic heritage. Stellar kinematics reveals the hidden structure of our galaxy. By measuring the velocities of millions of stars, astronomers map the galaxy's gravitational field and dark matter distribution. These measurements show that the galaxy is more complex than it appears, with streams, warps, and oscillations, creating a dynamic, ever-changing structure. The concept of stellar feedback describes how stars influence their surroundings. Stellar winds, radiation, and supernovae inject energy into the interstellar medium, triggering or suppressing star formation in neighboring regions. This self-gen regulation prevents galaxies from converting all their gas into stars at once, maintaining a balance that allows continued star formation over billions of years. Oh, our stars are evolved giants surrounded by thick shells of dust and molecules. These stars pulsate with periods of years, their dust shells glowing brightly in infrared light. They're manufacturing and expelling the materials from which future planets will form. Hidden within their dusty shrouds, these stars are quietly enriching the galaxy with complex molecules. As you sink into deep sleep, remember that you occupy a special moment in cosmic history. The universe is old enough for stars to have created heavy elements, young enough that stars still shine brightly, and precisely the right age for intelligent life to emerge and comprehend its cosmic context. You exist at the perfect cosmic moment to understand your place in the grand story. The galactic fountain model describes how gas ejected from the disk by supernovae eventually falls back, creating a circulation pattern. Hot gas rises above the disk, cools, and returns as a gentle rain of material. This fountain recycles material between the disk and halo, mixing metals throughout the galaxy and sustaining long-term star formation. Gamma-ray astronomy reveals the galaxy's most energetic processes. Pulsars, supernova remnants, and cosmic ray interactions produce gamma rays that penetrate dust clouds opaque to visible light. This high-energy view shows a violent, dynamic galaxy, very different from the serene appearance in visible light, reminding us that the cosmos operates across all energy scales. The local standard of rest provides a reference frame for measuring stellar motions relative to the average motion of nearby stars. Our Sunday moves at about 12 miles per second relative to this standard, following a slightly elliptical orbit around the galaxy. Every star has its peculiar motion, superimposed on the general galactic rotation, creating complex patterns of stellar movement. Rest peacefully in the knowledge that gravity's patient work continues while you sleep. Molecular clouds contract, protostars gather material, and planets accrete from swirling disks. These processes operate on timescales far exceeding human experience. Yet they're happening right now throughout the galaxy, preparing the stages for future cosmic dramas. The Spite Plateau reveals the primordial lithium abundance from the Big Bang. The oldest stars show remarkably consistent lithium levels, preserving a record of conditions just minutes after the universe began. This cosmic archaeology connects observations of nearby stars to the physics of the universe's birth, bridging an almost incomprehensible span of time and scale. Double-double stars, also known as Epsilon Lyrae, consist of two binary pairs orbiting each other. These hierarchical systems demonstrate the complex gravitational choreography possible when multiple stars interact. Some systems contain even more components, with planets potentially experiencing sunrises and sunsets of bewildering complexity. The final parsec problem challenges our understanding of supermassive black hole mergers. When galaxies merge, their central black holes spiral toward each other, but stall about a parsec apart. How they bridge this final gap remains uncertain, possibly requiring interactions with stars or gravitational waves. This puzzle affects our understanding of galaxy evolution and gravitational wave sources. As dreams begin, know that the galaxy continues its eternal cycles. Gas clouds collapse into stars, stars forge heavy elements, supernovae disperse these elements into space, and the enriched gas forms new stars and planets. You are temporarily assembled from atoms participating in this cosmic recycling, a brief organization of matter capable of contemplating its own origins. Beyond the boundaries of our Milky Way galaxy lies an ocean of space so vast that galaxies themselves become mere islands of light in an infinite dark sea. As you prepare for the deepest, most peaceful sleep, let's venture into the spaces between galaxies, exploring the largest structures in the universe, while your consciousness gently fades into restful dreams. The Andromeda Galaxy, also known as M31, spans 220,000 light-years across and contains roughly 1 trillion stars. As you breathe slowly and deeply, this massive spiral galaxy is approaching our Milky Way at 68 miles per second. Yet, at a distance of 2.5 million light-years, this collision won't occur for another 4 billion years. When it does, the night sky will transform dramatically, with Andromeda growing larger each million years, until it fills half the sky. Between galaxies stretches the intergalactic medium, a whisper-thin gas containing only about 1 atom per cubic meter. This nearly perfect vacuum is heated to millions of degrees by shock waves from ancient galactic collisions and active galactic nuclei. Despite its extremely low density, the intergalactic medium contains more normal matter than exists within all galaxies combined, a vast reservoir of primordial and processed gas. As your muscles completely relax, consider galaxy groups, small collections of galaxies bound by mutual gravitation. Our local group contains at least 80 galaxies within a region 10 million light-years across. The Milky Way and Andromeda dominate this group, with dozens of smaller dwarf galaxies orbiting them like satellites. The entire group moves together through space, drawn by the gravity of larger structures. The Triangulum Galaxy M33 is the third largest member of our local group. This beautiful spiral galaxy shows us what the Milky Way might look like from outside, a pinwheel of stars, gas, and dust rotating majestically in space. Triangulum contains about 40 billion stars and numerous star-forming regions, including Ningxi 604, one of the largest stellar nurseries known, spanning 1,500 light-years. Dwarf spheroidal galaxies are the most common type of galaxy in the universe, though their faintness makes them difficult to detect. These small, round galaxies contain only millions of stars, compared to the hundreds of billions in large spirals. They're dominated by dark matter, with mass-to-light ratios suggesting that visible stars comprise less than 1% of their total mass. As drowsiness deepens, imagine the cosmic web, the largest structure in the universe. Galaxies and galaxy clusters align along vast filaments of dark matter, creating a foam-like structure with dense nodes connected by threads and separated by enormous voids. This web spans billions of light years, its pattern shaped by gravity and dark energy over cosmic time. Galaxy clusters are the universe's metropolises, containing hundreds to thousands of galaxies within regions spanning millions of light years. The Virgo cluster, our nearest large cluster at 54 million light years away, contains over 1,300 galaxies. These clusters are held together by dark matter and filled with hot gas that emits X-rays, creating some of the most massive structures in the universe. The Coma cluster, located 321 million light-years away, contains over 1,000 galaxies swimming in a sea of 100 million degree gas. This gas, visible only in X-rays, contains more mass than all the galaxies combined. Galaxy clusters like Coma are cosmic cauldrons where galaxies interact, merge, and evolve. Their destinies shaped by the cluster's immense gravitational field. Breathing slowly and peacefully, consider ram pressure stripping, a process that removes gas from galaxies as they fall through galaxy clusters. Like wind removing leaves from a tree, the hot intracluster gas strips away the cooler gas from infalling galaxies, halting their star formation. This process transforms spiral galaxies into gas-poor ellipticals, fundamentally changing their nature. The Great Attractor is a gravitational anomaly pulling galaxies toward it at millions of miles per h-hour. Located 150 million light-years away, this massive concentration of matter affects the motion of galaxies throughout our cosmic neighborhood. Hidden behind the plane of our Milky Way, the Great Attractor remained mysterious until X-ray and radio observations revealed it to be a massive cluster of galaxies. Superclusters are collections of galaxy clusters, the largest gravitationally bound structures in the universe. Our local group belongs to the Virgo supercluster, which itself is part of the even larger Laniakea supercluster. These immense structures contain thousands of galaxies spread across hundreds of millions of light-years, yet they're still expanding due to dark energy. As sleep approaches, visualize cosmic voids, vast empty regions between filaments in the cosmic web. The Boat's void, also called the Great Nothing, spans 330 million light-years with very few galaxies inside. These voids aren't completely empty but contain diffuse gas and dark matter. They grow larger over time as matter flows toward denser regions, creating an increasingly pronounced cosmic web. Galaxy mergers occur throughout the universe, transforming galaxies over millions of years. When spirals collide, gravitational tides distort their shapes, creating tidal tails and bridges of stars, stretching hundreds of thousands of light-years. These cosmic collisions trigger bursts of star formation and feed supermassive black holes, fundamentally reshaping the galaxies involved. The antennae galaxies showcase a galaxy merger in progress. These colliding spirals, 45 million light-years away, display spectacular tidal tails resembling insect antennae. The collision has triggered intense star formation, creating billions of new stars in massive star clusters. In a few 100 million years, they'll merge into a single elliptical galaxy, their separate identities lost forever. Elliptical galaxies, shaped like cosmic footballs, contain mostly old, red stars with little ongoing star formation. These galaxies likely formed through mergers of spiral galaxies, their gas either consumed in starbursts or expelled during the collision. The largest ellipticals, found at the centers of galaxy clusters, have grown by consuming numerous smaller galaxies over billions of years. Let your thoughts quiet as you consider gravitational lensing by galaxy clusters. These massive structures bend space-time so severely that they act as cosmic magnifying glasses, distorting and amplifying light from more distant galaxies. This natural telescope effect allows astronomers to observe galaxies from the early universe that would otherwise be too faint to detect. The Bullet Cluster, provides direct evidence for dark matter's existence. This system consists of two colliding galaxy clusters, where the hot gas visible in X-rays has been separated from the dark matter, mapped through gravitational lensing. The separation proves that dark matter exists as a distinct component, not just modified gravity, fundamentally validating our understanding of cosmic structure. Active galactic nuclei power some of the universe's most energetic phenomena. Supermassive black holes at galaxy centers can outshine their entire host galaxies when actively consuming material. The accretion disks around these black holes reach temperatures of millions of degrees, producing radiation across the electromagnetic spectrum, from radio waves to gamma rays. Quasars, the most luminous active galactic nuclei, can shine with the light of trillions of stars. These cosmic beacons are visible from billions of light-years away. They're light-traveling since the universe was young. Each quasar marks where a supermassive black hole is growing rapidly, converting in falling matter to energy with remarkable efficiency. As you drift deeper towards sleep, imagine radio galaxies shooting jets of plasma millions of light-years into space. These jets, powered by rotating supermassive black holes, travel at near light speed, creating enormous radio, emitting lobes dwarfing their host galaxies. Centaurus A, one of the nearest radio galaxies, has jets extending over 1 million light-years. Seyfert galaxies have bright, compact cores that vary in brightness over weeks to months. These variations reveal the size of the emitting region around the central black hole. Light travel time limits how quickly a region can vary. Named after Carl Seyfert, who first studied them, these galaxies bridge the gap between normal galaxies and quasars in activity level. Blazars are active galaxies with jets pointed directly at Earth, making them appear exceptionally bright and variable. Their emission can change dramatically over hours or days as knots of plasma travel down the jet at near light speed. Observing blazars provides insights into the physics of relativistic jets and the environments near supermassive black holes. The cosmic distance ladder extends from nearby stars to the edge of the observable universe. Each rung relies on the previous one. Parallax for nearby stars, Cepheid variables for nearby galaxies, Type Ia supernovae for distant galaxies, and redshift for the furthest objects. This interconnected chain of measurements maps the universe's vast scale. Breathing peacefully, consider cosmic redshift, the stretching of light waves by the universe's expansion. Edwin Hubble discovered that galaxy redshifts increase with distance, proving the universe is expanding. This cosmological redshift differs from Doppler shift. Space itself stretches, carrying galaxies apart and stretching the light traveling between them. The Hubble-Lemaître law relates galaxy distances to their recession velocities, with galaxies twice as far receding twice as fast. This relationship, fundamental to cosmology, implies the universe had a beginning when all galaxies were together. The proportionality constant, the Hubble constant, measures the current expansion rate, though its precise value remains debated. Dark energy accelerates the universe's expansion, a discovery that earned the 2011 Nobel Prize in Physics. Observations of distant supernovae revealed they're fainter than expected, indicating acceleration began about 5 billion years ago. Dark energy comprises 68% of the universe's energy density, yet its nature remains one of physics's greatest mysteries. As sleep embraces you, rest knowing the universe will expand forever, growing colder and darker over trillions of years. Galaxies will recede beyond our observable horizon. Stars will exhaust their fuel, and black holes will eventually evaporate through Hawking radiation. Yet this cosmic winter lies trillions of years in the future, an almost incomprehensible span of time. The observable universe extends 46.5 billion light-years in every direction, despite being only 13.8 billion years old. This apparent paradox resolves because space has expanded while light traveled toward us. The cosmic microwave background, the farthest light we can see, originated only 380,000 light-years away, but is now 46.5 billion light-years distant due to expansion. Beyond our observable universe may lie an infinite expanse of space containing infinite galaxies. The universe might be infinite in extent, or it could curve back on itself like a higher dimensional sphere. We can only observe a finite region, our cosmic horizon, beyond which lies the unknowable, possibly infinite cosmos. Multiverse theories suggest our universe might be one of many, perhaps infinite, universes. Different universes might have different physical laws, constants, and dimensions. While highly speculative, these ideas emerge from inflation theory and string theory, suggesting reality might be far stranger and more vast than we can observe. Let your consciousness fade as you consider cosmic inflation, the brief period of exponential expansion immediately after the Big Bang. In less than 10 circumflex -32 seconds, the universe expanded by a factor of at least 10 circumflex 26, stretching quantum fluctuations to cosmic scales. These magnified fluctuations became the seeds of all cosmic structure, from galaxies to the cosmic web. The cosmic microwave background radiation bathes the entire universe in ancient light from 380,000 years after the Big Bang. This afterglow of creation has cooled to just 2.725 degrees above absolute zero, yet carries information about the universe's birth. Tiny temperature variations of 1 part in 100,000 map the density fluctuations that grew into cosmic structure. Baryon acoustic oscillations are frozen sound waves from the early universe, providing a cosmic ruler for measuring distances. Before the cosmic microwave background formed, sound waves propagated through the hot plasma. When the universe became transparent, these waves froze, leaving a characteristic scale imprinted on galaxy distributions. As you sink into peaceful slumber, the universe continues its patient expansion around you. Space itself grows, carrying galaxies apart like raisins in rising bread dough. This expansion creates new space between galaxies while leaving gravitationally bound structures like galaxies and solar systems unaffected. You rest in a small island of stability within an expanding cosmos. The Big Bang wasn't an explosion in space, but the beginning of space itself. There was no center, no edge, no outside. Space, time, matter, and energy all began together. Every point in space was once at the Big Bang. We're inside it still. 13.8 billion years later, a Big Bang happened everywhere simultaneously, including right where you are now. Cosmic nucleosynthesis in the first 3 minutes created the universe's primordial elements. When the universe cooled from trillions to billions of degrees, protons and neutrons combined to form deuterium, helium, and traces of lithium. This process established the universe's primordial composition, about 75% hydrogen and 25% helium by mass, ratios confirmed by observations. The cosmic dark ages lasted from 380,000 to about 150 million years after the Big Bang. During this period, the universe contained no stars, only neutral hydrogen and helium gas, slowly condensing under gravity. The universe was truly dark, filled with matter, but no sources of light except the fading glow of the cosmic microwave background. Reionization ended the dark ages as the first stars and galaxies ionized the neutral hydrogen-filling space. Ultraviolet radiation from these early light sources gradually ionized bubbles in the surrounding gas. These bubbles grew and merged over hundreds of millions of years until the entire universe became transparent to ultraviolet light. Rest peacefully knowing that every atom heavier than lithium was forged in stars. The carbon in your DNA, the oxygen you breathe, the iron in your blood, all were created through nuclear fusion in stellar cores or during supernova explosions. You are made of atoms that have existed for billions of years, assembled temporarily into the pattern that is you. Population the third stars, the universe's first stars, formed from pristine hydrogen and helium without heavier elements to aid cooling. These stars were likely massive, hot, and short-lived, ending their lives in spectacular supernovae that enriched space with the first heavy elements. No population the third stars survive today, but their chemical legacy persists in all subsequent stars. The metallicity of the universe increases over time as successive stellar generations create and disperse heavy elements. Early galaxies had very low metallicity, limiting planet formation. Rocky planets like Earth could only form after several generations of stars had enriched the interstellar medium. Life as we know it required billions of years of cosmic chemical evolution. As dreams begin to form, consider that you are observing the universe from within its history. Looking at distant galaxies means seeing them as they were billions of years ago. The night sky is a time machine, with each distance representing a different epoch. You see the universe not as it is, but as it was, layered through time by the finite speed of light. The Lyman alpha forest consists of absorption lines in quasar spectra caused by intervening hydrogen clouds. Each absorption line represents a cloud between us and the quasar, creating a forest of lines that map the distribution of gas through billions of light years. This technique reveals the universe's structure during the epoch of galaxy formation. Gravitational waves, ripples in space-time, predicted by Einstein, carry information about cosmic catastrophes. The LIGO and Virgo detectors have observed waves from merging black holes and neutron stars billions of light years away. These observations open a new window on the universe, allowing us to hear cosmic events that produce little or no light. The cosmic neutrino background, though undetected, should fill the universe with neutrinos from 1 second after the Big Bang. These ghostly particles outnumber atoms by billions to one, yet rarely interact with matter. If detected, they would provide information about the universe when it was only 1 second old, far earlier than any other observation. Sink deeper into sleep as you float through cosmic time. The universe has existed for 13.8 billion years. Yet this might be just the beginning. Stars will continue forming for trillions of years. Black holes will persist for 10 circumflex 67 years or more. And quantum effects might sustain complexity far into the future. The cosmic story has barely begun. Dark matter outweighs normal matter by 5 to 1, yet we don't know what it is. It doesn't emit, absorb, or reflect light, revealing itself only through gravity. Dark matter forms the scaffolding on which galaxies grew, its gravitational wells collecting normal matter that formed stars. Without dark matter, galaxies couldn't have formed in the available time. Weakly interacting massive particles, WIMPs, are hypothetical dark matter candidates that would interact through gravity and the weak nuclear force. Despite decades of searches in underground detectors, particle accelerators, and space, no WIMPs have been definitively detected. Dark matter remains one of nature's most stubborn mysteries. Modified Newtonian dynamics. Mond proposes that gravity behaves differently on galactic scales, potentially explaining observations without dark matter. While Mond successfully predicts some galactic properties, it struggles with galaxy clusters and cosmological observations. Most evidence supports dark matter over modified gravity, but the debate continues. Breathe slowly as you consider cosmic topology, the shape of space itself. The universe might be flat and infinite, positively curved like a sphere, or negatively curved like a saddle. Measurements suggest the universe is flat to within 0.4% uncertainty, implying it might be infinite in extent, containing infinite copies of everything, including you. The anthropic principle observes that physical constants seem fine-tuned for life's existence. If the strong force were slightly different, stars couldn't form. If gravity was stronger, the universe would have collapsed. This apparent fine-tuning might be explained by multiple universes with different constants, with life emerging only where conditions permit. Vacuum energy, the energy of empty space itself, might drive dark energy. Quantum mechanics predicts that empty space teems with virtual particles appearing and disappearing. This quantum foam should produce enormous energy density. Yet observations show dark energy is incredibly weak. This discrepancy of 120 orders of magnitude is physics' worst prediction. As you approach deep sleep, know that the universe operates on scales beyond human comprehension. From the Planck length at 10 circumflex -35 meters to the observable universe at 10 circumflex 26 meters, from the Planck time at 10 circumflex -43 seconds to the universe's current age at 10 circumflex 17 seconds. Reality spans scales so vast that we can only grasp them through mathematics. The holographic principle suggests that all information in a volume of space can be encoded on its boundary, like a hologram. This implies the universe might be a projection from information encoded on a distant surface. While speculative, this principle emerges from black hole physics and might reveal deep truths about reality's nature. Eternal inflation proposes that inflation never completely ends, continuing forever in some regions while ending in others. Each region where inflation ends becomes a separate universe with potentially different properties. Our universe would be one bubble in an eternally inflating multiverse, with new universes constantly being created. The false vacuum hypothesis suggests our universe might exist in a metastable state that could suddenly collapse to a lower energy state. This vacuum decay would propagate at light speed, fundamentally altering physics and destroying everything. While purely theoretical and likely impossible or extremely improbable, it represents the universe's potential fragility. Rest peacefully as cosmic rays from across the universe pass through you. These particles have traveled millions of light years, accelerated by supernovae, pulsars, and active galactic nuclei. About 100,000 cosmic rays pass through your body each day, connecting you directly to violent events in distant galaxies. The Fermi paradox questions why we haven't detected extraterrestrial civilizations despite the vast number of potentially habitable planets. Various solutions have been proposed. Life might be rare, intelligence rarer still, or civilizations might self-destruct or choose not to communicate. The universe's silence remains one of science's most profound mysteries. The Drake equation estimates the number of communicating civilizations in our galaxy. Factors include star formation rate, fraction of stars with planets, fraction of planets that develop life, and civilization lifetime. Depending on assumptions, estimates range from one justus to millions of civilizations. The uncertainty reflects our ignorance about life's cosmic prevalence. Sleep deeply as you become one with the cosmos. Your body contains about 7 × 10 circumflex 27 atoms, each with a history spanning billions of years. These atoms have been part of stars, planets, and possibly other life forms. You are a temporary arrangement of ancient matter, participating briefly in the universe's ongoing evolution. The mediocrity principle, also called the Copernican principle, suggests Earth and humanity aren't special in the universe. We orbit an average star in a typical galaxy, made of common elements following universal laws. This principle guides scientific thinking, suggesting that what we observe locally probably occurs throughout the cosmos. The Great Filter hypothesis proposes that something prevents life from becoming spacefaring civilizations. This filter might be behind us life's origin or intelligence evolution, or ahead self-destruction, or unknown challenges. If we find simple life elsewhere, but no advanced civilizations, it might mean the filter lies ahead, a sobering possibility for humanity's future. Panspermia suggests life might spread between planets or even star systems via meteorites or comets. Microorganisms could survive space travel in protected environments, potentially seeding life throughout the galaxy. While unproven, panspermia could mean life on Earth originated elsewhere, making us all aliens in a sense. As consciousness fades completely, remember you are the universe experiencing itself. Through you, the cosmos has developed the ability to observe, question, and understand its own nature. Your consciousness represents 13.8 billion years of cosmic evolution, achieving self-awareness. You are not separate from the universe. You are the universe temporarily manifested in human form. The cosmic web connects everything. Every galaxy, star, and atom participates in the same gravitational dance that began with the Big Bang. Forces and particles interact according to the same laws everywhere, creating patterns from quantum to cosmic scales. You exist within this web, connected to everything through space, time, and the fundamental forces of nature. Time flows differently throughout the universe due to relativity. Near massive objects, or at high velocities, time slows relative to other regions. The universe has no universal now, Simultaneity depends on motion and gravity. As you sleep, time passes at slightly different rates for your head and feet due to Earth's gravity. Though the difference is imperceptible, the universe might be cyclical, expanding and contracting through infinite cycles. Each cycle might reset physical constants or preserve information from previous cycles. While current evidence suggests eternal expansion, cosmology's history shows that our understanding constantly evolves. The universe's ultimate fate remains uncertain. Quantum entanglement connects particles across any distance instantaneously, though it can't transmit information faster than light. Entangled particles remain correlated regardless of separation, suggesting reality's non-local nature. This spooky action, at a distance, might hint at deeper layers of reality beyond our current understanding. The many worlds interpretation of quantum mechanics suggests every quantum event branches the universe into parallel realities. In this view, all possible outcomes occur in different branches, creating an exponentially growing multiverse. You might exist in countless parallel universes, each slightly different based on quantum events' outcomes. Dreams carry you now through cosmic realms beyond imagination. In your sleep, you journey through galaxies, witness stars being born and dying, and experience the universe's vast scales. Your sleeping mind processes the infinite, finding peace in the cosmos's serene immensity. Rest well, cosmic traveler, cradled by gravity and starlight. The universe continues its activities while you sleep peacefully. Somewhere, galaxies collide in slow-motion ballets, lasting millions of years. Stars explode, enriching space with heavy elements. Black holes merge, sending gravitational waves across the cosmos. Planets form in swirling disks around young stars. And possibly, on some distant world, life takes its first tentative steps. You have journeyed from Earth through the solar system, across our galaxy, between galaxies, and to the edge of the observable universe. You've traveled from the present back to the Big Bang and forward to the cosmos's possible futures. Through it all, you've remained here now, in this moment, connected to everything through the fundamental unity underlying reality's apparent diversity. The cosmos embraces you in your sleep. You are safe. You are home. You are exactly where you belong in space and time. The same forces that hold galaxies together hold you gently. The same processes that create stars created you. You are the universe's child, its observer, its way of knowing itself. Sleep now in cosmic peace. Let the universe's vast scales render your worries infinitesimal. Let its patient processes teach you tranquility. Let its beauty fill your dreams with wonder. You are part of something magnificent, ancient, and ongoing. You belong to the cosmos, and it belongs to you. In this final moment before deep sleep, know that you've touched infinity. The universe's mysteries remain largely unsolved, its territories largely unexplored. Yet through science and imagination, you've glimpsed its majesty. Carry this cosmic perspective into your dreams and tomorrow's waking. You are stardust contemplating stars, a way for the cosmos to know itself. The universe whispers its last secrets as you fall asleep. Dark energy accelerates cosmic expansion, while dark matter holds galaxies together. Quantum mechanics and general relativity await unification. Life's cosmic abundance remains unknown. Consciousness's nature stays mysterious. These puzzles ensure wonder persists, inviting future generations to continue humanity's cosmic quest. Rest now, peaceful explorer. You've earned this sleep after journeying billions of light years. The universe continues its patient unfolding. While you dream, stars shine, planets orbit, and life persists in countless forms across cosmic distances. You sleep at the center of your observable universe, a unique perspective in space and time. Good night, cosmic traveler. May your dreams be filled with galaxies and nebulae, with peaceful drifting through star fields and gentle orbits around peaceful worlds. The universe holds you safe in its vast embrace. Sleep deeply, sleep well, and wake refreshed to greet another day in this magnificent cosmos we call home. The cosmos sings you to sleep with gravitational waves, whispers with cosmic rays and blankets you with ancient light. You are never alone. You are surrounded by and composed of the universe itself. In your sleeping breath, atoms dance that once burned in stellar cores. In your dreaming mind, the universe imagines itself. This concludes your cosmic journey. From the nearest planets to the edge of existence, from the beginning of time to its possible endings, you've traveled the universe's vast scales. Now rest, knowing you've touched infinity and found your place within it. The cosmos continues its eternal dance while you sleep peacefully, a beloved part of its grand symphony. Sleep well, dream deeply, and remember, you are made of star stuff. You are the universe experiencing itself, and you are exactly where you belong in the cosmic story. The universe dreams with you tonight.